So here we have the 2010 Pulley question. Now we've got two particles that are connected by an inextensible string. So the system is released from rest and we're asked to work out the tension in the string. What we have to think about here are the forces involved. Now there's a force that's common to the two things, so I'll do one in blue here. Do them both in the same colour actually would make sense. So that's the tension that this block will feel, and it'll be the exact same as the tension as this one will feel. So that's the tension in the string because they're connected. Now what will also happen is that we've also got the force of gravity happening to both of them. So I'll do them both in green. The force of gravity for this block pulling down this way, and then the force of gravity in this block pulling down this way wouldn't be quite as great because this one's heavier. So I'll just fill in because we know what they are. So this is the force of gravity of this one. That green force there, I'll leave it at green, we'll go with, is mass times gravity. For this one it's 0.25 g. For this one it's mass times gravity again, but in this case it's only 0.24 g. So those are, if you just think about it, that's if it's just as it's at rest, just immediately after you release it. Those are the four forces that you can see. Now what will happen when it's released from rest? Well, what will happen is, you'll probably think of it intuitively, is that this here, this system over here will move down, while this one over here will move up, and this one will move down. So what we think about is how we understand how they're going to move. It'll be to do with the net force. So we've got this tension here, they're the same. The forces of gravity are different. We know that this system on the right hand side, and I'll do it in red, will overall have force of acceleration due to, it'll accelerate, and I'll just do it in red. So this is going to accelerate, and then this will be mass times acceleration. So in this case it'll be the mass, which is 0.25 a, while this side here will net accelerate, will go up like this here, the exact opposite of that one there, and it'll be mass times acceleration, but in this case it'll be 0.24 a. Now we can use these two systems, the two things I've got highlighted here, to work out, to get two equations. Now I'll just try to make it as obvious as possible. This green vector here, actually I'll undo that line, I'll do it with a lighter pen. This green line here, that vector minus that vector will be equal to this vector. Okay, so I'll just put that into I'll just write it out. So we've got mg, which would be 0.25 g, minus the tension will be equal to 0.25 a. That's our first equation. Let's redo that one there because it's not very clear. Call that equation 1. We also know that we've got and I'll just do this one, it's very similar, so that's equation 1. Now I'll go for this second box here and I'll do them out again. We also know that in this case, and I'll just try to show it here, so this tension here minus this one here will be equal to this overall acceleration vector here. So I'll write that equation out. So in this case, it's going to be the tension minus 0.24 G is equal to 0.24 A. Okay, that's our equation 2. So now that we've got our two equations, we just have to work them out. There's a number of different ways you can do this. It's simultaneous equations is one, but what we could do is just, if we find a value for, if we use equation 1, if I rearrange equation 1 and just get t in its own. So from equation 1, we'd have, I'll just do it all in blue, we could, I'll just write it out again, 0.25 G minus t is equal to 0.25 A. So bring t or getting t in its own, so we'd have 0.25 G minus 0.25 A is equal to t. Now, we can sub this into equation 2. So you've got 0.25 G minus 0.25 A minus 0.24 G is equal to 0.24 A. Not very clear there, just at 0.24 A. Now, 0.25 G minus 0.24 G is the same as 0.01 G. When you bring that one over and add it to that side, you'll have it is equal to 0.49 A. So we have a value for A. A is equal to 0.01 G over 0.49. Now, when I see 0.49 like this, I'll always be thinking that, because it comes up quite a lot, when we're dealing with G, we can take, in the higher level, we'll take G as 9.8. So if you look at 0.49, we'll divide into 9.8 exactly 2 times. So we'll have, I'll just rewrite the whole thing there, 0.01 times 9.8 over 4.49. 0.49 will divide into 9.8 exactly, well, 20 times. So it'll be equal to 0.01 times 20, which is equal to 2. Nothing. 0.2 meters per second squared. Okay, so now we've got the acceleration. I'll start working up over here. There's loads of room over this side. We can then work the tension. So if we use equation 1, we've got 0.25 G minus the tension is equal to 0.25 A. Bring over the T, bring over the, well, we know that the tension is equal to 0.25 G minus 0.25 A, which is equal to 0.25 G minus A. Just to do a little bit, easier, so there'll be less calculations involved. Which would 9.8 minus 0.25 times 9.6, the same as a quarter of 9.6. 4, that goes twice, carry the 1. 2.4 newtons. That's what our tension is equal to. That's part 1 complete. Now part 2 is a good bit easier. We just need to find the speed of the two masses when the 22.25 kilogram masses descend at 1.6 meters. So I'm going to do this in black just so that we can see the difference between these two parts of the question. Now, for this one, we know the acceleration. We worked it out at 0.2 meters per second squared. We know the initial velocity. It starts from rest. we know the displacement is equal to 1.6 meters, and what we're asked for is the speed of the two values is v. What is v? We'll write out our three equations. So we've got v is equal to u plus at, v squared is equal to u squared plus 2as, s is equal to ut plus 1/2 at squared. There's a fourth one, I won't include it here, I don't think we need it. We're looking for v, we're given u, a and s, so it's quite obvious we want to use the second equation. And I'll just make a bit of space for myself here. So using this one, we have v squared is equal to u squared, which is 0, plus 2as. V squared is equal to 2 times acceleration, 0.2 times 1.6. So it's 0.4 times 1.6, 24, 2, 4, 64. So it'll be 0.64. Is that correct? 0.4 times 1.6, 0.64. 0.4 times 1.6. Yeah, that looks right. So v is equal to the square root of 0.64, which is equal to, I think it's 0. Well, I'll just double check it. It'll take a second. I should know that offhand. So it's the 0.64 to the power of a half by 5 is equal to 0.8. That's what I thought it was, but just wasn't sure. Okay, so that's our sum done.